Hello, my name is Han Yang, and I'm from Beijing Institute of Technology. And today I'll be presenting our work using blockchains for censorship-resistant bootstrapping in anonymity networks. Internet surveillance has become prevalent as more of our regular activities shift online. Public concerns over privacy have been likely at one of their peaks. So our work uses Tor as a case study, and if you are not familiar with Tor, mm, Tor is a useful privacy-enhancing tool that allows millions of users around the world to use the internet privately and to circumvent censorship. And how are users able to do that? Well, in order to access information and services on the destination server, a user will create a path to the Tor network to route their traffic. Tor then forwards internet traffic through a source-routed path, constructed by typically three relays called a circuit. A Tor circuit is a combination of entry, middle, and the exit relay. That is a key component of Tor which appends to any routing. In other words, encrypted traffic enters the network at an entry guard relay, where guards are relays that are faster and stable compared to other relays. And the second hop in a circuit is the middle relay, which carries traffic to the exit relay that acts as the egress point of Tor. And in order to enable clients to automatically obtain up-to-date information on the state of the network, Tor introduces a set of directory authorities to keep the network status. They hourly vote and generate a document, which we call the consensus, listing all currently active relays in the network, and all clients need to download this consensus. Censorship of the Tor network is possible, and many governments have completely blocked the anonymity service. Generally, censors block the Tor network in two ways. On the one hand, censors can easily block connections to public Tor relays based on the IP addresses listed in the publicly available consensus. On the other hand, the characteristics of Tor traffic are fingerprintable. Therefore, censors can prevent any network traffic that looks like Tor communication. So in order to get around the censors, Tor uses bridges and pluggable transports. Tor bridges are alternative entry relays whose IPs are not published in the consensus, with the Tor project sending out a call for running a bridge last year. The number of bridges has significantly increased to about 2,600. And pluggable transports transform auto traffic between a client and the bridges to look similar to other innocuous traffic so that it's not identifiable. There are a lot of PTs, such as OBFS4, MIC, and Snowflake. However, these tools are also subject to blocking and surveillance. For example, MIC uses a technique called domain fronting to hide Tor traffic inside the encrypted payload of an allowed HTTPS connection. Unfortunately, domain fronting has been shut down by many CDNs, such as Amazon and Google, which makes MIC much less effective. And the Snowflake is a new way, but clients still require domain fronting to access the broker and often experiences slower speeds. In reality, There are nearly 10 times more clients connecting by OBFS4 than by Mic or Snowflake. Consequently, for most Tor clients, obtaining bridges is a major challenge. Basically, the Tor software has a number of built-in default bridges. However, they are often far more brittle compared to the public Tor relays, and their IPs are hard-coded in the Tor browser, leaving them vulnerable to censorship as well. For better secrecy, Tor clients can also request custom bridges, as shown in the figure, similar to directory authorities keeping a list of available public relays. Tor introduces a bridge authority, which we call BOS, to collect running bridges in the network. BOS sends information about new bridges to BridgeDB after testing their reachability. Afterwards, BridgeDB assigns and distributes Tor bridges based on client requests. And BridgeDB currently supports 3 channels for clients to get custom bridges: visiting its website, sending it an email, and using mode to fetch from within the Tor browser. Clearly, the first 2 channels, HTTPS and email, are blocked by censors, but mode is an effective tool that uses domain fronting to stealthily transmit sensitive data. However, mode not only relies on the ongoing support of CDNs, but doesn't make clients anonymous or completely hide their destination. In summary, all these ways may compromise the anonymity of users due to identity exposure and remain challenging for clients located in certain heavily censored areas. So in this work, we propose a new practical and more decentralized distribution channel for Tor bridges to mitigate the threat of blocking without degrading Tor users' anonymity. Instead of trusting centralized CDN providers, our architecture uses a blockchain system that doesn't require any additional trust. Well, what is a blockchain? A blockchain is a data structure which consists of a continuously growing list of data blocks. The data blocks are linked together such that old blocks can't be removed or altered. And essentially, a blockchain is an implementation of a distributed ledger. All blockchain nodes adopt a distributed consensus algorithm to guarantee data consistency. There are 3 types of current blockchains: public, consortium, and private. A public blockchain allows anyone in the world to participate in the consensus process without the need for a trusted third party, and is secured by economic incentives and cryptographic verification. However, consortium and private blockchains tend to limit the read and write permissions of participants by including trusted entities and are therefore not fully decentralized. And when we explain the benefits of the public blockchain, we often list a few key features such as decentralization, transparency, security, immutability, and censorship resistant. Well, we argue that censorship resistance is seen as one of the value propositions of cryptocurrencies because there is a financial incentive to protect stored data and thousands of copies for verification and redundancy. In fact, the use of blockchain for censorship resistance has drawn the attention of researchers. We call our blockchain-based bridge distribution solutions Antiblok. Antiblok retains Tor BOS and BridgeDB, while using a public blockchain to act as an anonymous and censorship-resistant distribution channel for bridges. The figure shows the Antiblok model and the bridge distribution workflow, involving 6 components. A Tor client is a user who can't connect to the Tor network due to the blocking and thus seeks a bridge to evade censorship. These clients typically need an unblockable channel because they have no means to access dedicated servers offered by the Tor project such as BridgeDB. A bridge refers to an unpublished Tor relay that facilitates entry to anonymity networks for blocked clients. Volunteers can register at BOS as a bridge operator and then upload their bridge information. The censored service is the destination of the client circuit and is likely to be monitored or blocked without the use of anonymity networks such as Tor. The bridge authority aggregates information from bridges, checks their cryptographic validity and port reachability, and sends information about available bridges to BridgeDB. The BridgeDB is a collection of servers for assigning and distributing bridges to Tor clients. In addition to the three existing transmission channels for bridges, it should prevent an anonymous and hard-to-block channel to clients located in censored areas. Finally, the public blockchain offers a covered channel in the form of blockchain transactions. The bridge information used to bootstrap clients to the anonymity network is embedded in transactions that are recorded in the public ledger. And in short, the primary aim of Antiblok is to allow Tor clients inside censored areas to successfully learn available bridges and reliably route their traffic to the destination website via three voluntarily participating public or secret relays while keeping the anonymity of requesting clients. Therefore, we design a request response mechanism in the blockchain framework. As the requester, the client sends the request transaction to the blockchain. BridgeDB is the responder, which consistently retrieves the request transaction from the distributed ledger. Once BridgeDB finds a new request, it will send a response transaction with embedded bridge information. Finally, the client gets the data from the response transaction. So in this model, we adopt Tor's threat model, a non-global adversary that can control a fraction of all relays and probably see the traffic at one end of a circuit but can't observe the entire network. More importantly, we consider a sensory adversary that attempts to block or monitor the communications between clients and blockchain nodes. However, we assume that the censor is reluctant to block or significantly hinder the use of public blockchains. Even in a heavily censored area, censoring a public blockchain with a market capitalization would come at an unaffordable economic cost. Also, we assume that the censor doesn't have the resources to control more than 51% of the mining power in a public blockchain. I will then introduce the details of Antiblok's protocol. Firstly, BridgeDB's public keys are broadly distributed, but corresponding private keys are kept secret and only BridgeDB knows them. And Antiblok requires Tor clients to create a one-time blockchain account for every request. The private key of this account is determined between the client and BridgeDB via ICICS agreement. Well, the key strength of this account sharing design is that no payment interaction is required, and the identity of the client is anonymous due to the pseudo identity. In addition, all communications between clients and BridgeDB occur over the blockchain transaction, and a request transaction is sent from a user address to the shared address. The unobservability of transactions is enhanced by randomness of addresses. Note that the user address shouldn't be linked to other activities in order to avoid user privacy from being inferred. So the source of its balance needs to be untraceable. There are many ways to quickly and easily buy ICE anonymously, such as Ether ATMs. On the other hand, a negotiation-based account reduces the difficulty for Tor clients to receive data, since Antiblok enables the client to receive bridges only from the input field of the transaction sent from the known account, as we will see later. We suggest that BridgeDB runs an Ethereum node to hold a copy of the up-to-date public ledger to constantly retrieve whether a new transaction carrying a request has been sent. So, once a new block is added to Ethereum, BridgeDB gets all the transactions it contains and checks if any of them carry requests. For a successful retrieval, BridgeDB can tickle the secret message from its input field, then pass it into two parts, and finally compute the private key and address. Note that the computed address must be equal to the output address of the request transaction. Otherwise, it fails on address verification. Finally, BridgeDB decodes the encrypted user's public key with its private key into plain text that will use to encrypt the bridge information. And then BridgeDB assigns a subset of bridges upon request and providers clients with them, since all transactions in a public blockchain are open and traceable. Information about top bridges must be cryptographically protected. Antiblok adopts a public key encryption algorithm to encrypt bridge information into encrypted data. Unlike the request transaction, the response is a contract transaction, which is sent from the shared address to a random smart contract address. Note that the smart contract is not predefined, but is dynamically selected by BridgeDB based on the up-to-date Ethereum ledger. So the encrypted bridge data is concealed in the data of random smart contracts. As mentioned above, Tor clients only retrieve transactions sent from the address of shared accounts, and a client can fetch the encrypted bridge data from the input field of transaction 2. Even if it's not yet included in a block, the client then extracts the ciphertext and decrypts it with its private key to obtain custom bridges. Finally, the client will connect to a bridge using a pluggable transport. After successful establishing a circuit, the client will route its traffic to censored services using the constructed circuit. Our evaluation aims to show whether Antiblok helps censored Tor clients get bridges and how much time cost will incurred by introducing Ethereum. For BridgeDB, we manually simulate the assignment and the distribution workflow in Antiblok. We start by applying for OBFS4 type bridges on BridgeDB's website based on the IP address. Then, once a request transaction is retrieved, we take 3 bridges as an assignment result and transmit them to the client covertly via an Ethereum transaction. The simulated client within the censored area runs on a cloud instance created in Beijing with CentOS and Tor browser installed. We know that congestion often occurs in the Ethereum ecosystem due to a large number of transactions. In the worst case, the congestion will last for many days, which certainly affects the availability of Antiblok. However, an Ethereum-based channel is still more reliable than fundamentally blocked distribution channels, since blockchain systems always have the ability to self-mitigate. In order to evaluate the ability of Antiblok to bypass client-side blocking, we use RakenB testnet as a communication medium between the censored client and BridgeDB. In practice, most testnets select only a small number of nodes to validate transactions and create blocks, so their transaction frequency tends to be lower than that of the mainnet. The implementation details of Antiblok in Ethereum are offered above. In summary, BridgeDB embeds the request and response messages into two Rikenby transactions respectively. The average time for every process of bridge distribution workflow is shown in the table, while the procedure for adding the request transaction to a block is limited by the Ethereum itself. The total time of Antiblok is about 22 seconds, which is acceptable as it doesn't have to be real-time. All in all, Antiblok bypasses client-side blocking of bridge distribution in Tor by using blockchain transactions as rendezvous, and is targeted at anonymously providing censored clients with bootstrapping information. And we make three main contributions. Firstly, we propose a novel bridge distributor for the Tor network. By using a public blockchain as a covered channel, clients can bypass blocking without degrading their anonymity and unlinkability. Secondly, we design a negotiation-based account sharing mechanism that allows clients to not interact with addresses publics related to Tor, such that distinguish special transactions from normal transactions is far more difficult. Finally, we implemented and evaluated Antiblok on the Ethereum Rikenby and showed that it can help censored clients to fetch information about Tor bridges. Well, that's all. Thanks for listening.